Hello, my name is Shahriari, and this is a lecture in a series of lectures on introductory linear algebra based on my book, Retrolinear. The subject of this lecture is vector spaces. What are they and why do we study them? And this is the first lecture in a systematic study of vector spaces. We want to start by reminding you of some examples of vector spaces, seeing what they have in common, and using that to define what a vector space is. In fact, I have videos on each one of these separately, but I'm going to remind you of the examples that from them we abstract this notion of vector spaces. Our prototypical example is Rn. R3, for example, it's points in three-dimensional space. Elements of R3 are triples of real numbers, and you can write them as a row vector or as a column vector. One element of R3 is something like 1, 5, minus 47. That triple is just one element of R3. And the games we can play in R3 are addition and scalar multiplication. We can multiply any one of these elements by a scalar, by a real number, or we can add two of them and we get another one of them. The same thing is true of polynomials. This is another world where we have the same kinds of games. If n is a non-negative integer and we have n plus 1 real numbers, then we make a polynomial, a0 plus a1x plus a2x squared plus all the way till a and x to the n. If those coefficients are real numbers, that's a polynomial in x with coefficients in real numbers. The notation r bracket x or p of r is going to be the set of all polynomials in x with coefficients in r. We have addition, we can add two polynomials, and we can multiply by scalars. We have other things we can do with polynomials, like we can multiply two polynomials, but that's not what we're going to focus on now. For vector spaces, we focus on addition and scalar multiplication. Matrices are another example. If m and n are positive integers, an m by n matrix is a rectangular array of numbers with m rows and n columns. Now, r to the m times n, or m sub m by n r, is the set of all m by n matrices with entries from R. And again, we can multiply those by scalars. How do you multiply a matrix by a scalar? You take a real number and multiply it by every entry. You can also add two matrices that are of the same size, and you do that by adding the corresponding entries. Again, I have a whole video on matrices and the notation about them. So watch that if you're not familiar with them. Now, what is a vector space? If V walks through the door, how do you know if it's a vector space or not? So V has to be a non-empty set, and you have to be able to add elements of V. That means that you have to be able to add two elements of V and get an element of V. The way we write that is that for x and y in V, there exists a unique element x plus y in V. There should be no ambiguity. If you give me x and y, I should be able to tell you what x plus y is. You have to be able to multiply an element of V by a scalar. First time through linear algebra, that means a real number, but later we will complicate that a little. Given x in V and alpha a real number, there should be a unique element alpha x, which is also element of V. Addition and scalar multiplication may be familiar or not. For example, for matrices, polynomials, and Rn, they were familiar things that sort of made sense. But whatever they are, they must obey certain rules. These rules do not seem profound, but they're abstracted from the examples that we saw from Rn, polynomials, and matrices, and have to be checked and followed. You have to make sure that those rules are followed if you want to make sure that V is a vector space. Sometimes that's obvious, like you say, okay, yeah, I know these rules are followed because this is a very natural addition and scalar multiplication. Sometimes they're not. So a vector space, again, is a set of elements with two games, addition and scalar multiplication, that follow certain rules. But what are those rules? The properties that addition must have is the following. As I said, that you have to be able to add elements and get another element, but you can't just do it willy-nilly. It has to follow certain rules. The addition has to be commutative, so x plus y should be the same as y plus x. It has to be associative. X plus y plus z should be the same as x plus y plus z. And there should be some element among all the elements that's called the zero vector. And how do you know that you have a zero? You have a zero if that guy who claims to be zero, if you add it to other things, nothing happens and you get that other thing back again. So x plus 0 should be x. It's not that someone can just declare I'm a zero. They have to pass this test. It has to be that when you add them to other things, nothing happens. Also, there has to be negative. So for every element, there got to be a friend, or maybe it's better called enemy, that when you add it, you get the zero. For every element in your vector space, you have to have some other element that when you add them, you get zero, and that other element we call minus x. Now, scalar multiplication also has to have four properties. If alpha and beta are real numbers, are scalars, and x and y are elements of the vector space, you need a couple of distributive laws. Alpha times x plus y should be the same as alpha x plus alpha y. If you take a scalar alpha and multiply it by the sum of x and y, we should get the same answer as if you multiplied by x and y and then added them. Alpha plus beta times x should be alpha x plus beta x. Alpha beta times x should be the same as alpha times beta x. And finally, the scalar one, the number one, if you multiply it by any x, you should get x back again. This upside A means for all x in V, for everything. In fact, all of these are true for all x and y in V, and for all real numbers alpha and beta. I'm going to say this one more time because this is our fundamental definition. V is a non-empty set, and assume that for every x and y, there exists a unique element x plus y in V, such that x plus y is y plus x plus y plus z is x plus y plus z. For all x and y and z in V, there exists this element 0 in V. If you add x to 0, you get x for any x in V. And for all x in V, you've got a negative that if you add it to x, you get 0. Also, you can multiply by scalars, and that follows the rules that we mentioned before. Alpha times x plus y is alpha x plus alpha y. Alpha plus beta times x is alpha x plus beta x. Alpha beta times x is alpha times beta x, and 1 times x is x. The point is that if something walks through the door and says I'm a vector space, this is what you have to check. You have to check that you have an addition and you have a scalar multiplication, and then in addition to that, you have 4 rules that you have to check for addition and 4 rules for scalar multiplication. If you have all of these things, then V is a vector space over R. The over R part is you're telling me what the scalars are, and they are real numbers. Elements of V are called vectors, and elements of R are called scalars. So what's a vector? It's an element of a vector space. And so it could be a matrix, a polynomial, or an element of Rn. So what are examples of vector spaces over R? Rn, n tuples with entries in R, and here addition and scalar multiplication is that of n tuples. R infinity, infinite sequences of real numbers, addition and scalar multiplication of infinite sequences. Polynomials with real coefficients, using addition and multiplication of polynomials. Polynomials of degree less than or equal to n. Those also form a vector space, because if you take polynomials of degree less than or equal to n and add them, you still get a polynomial of degree less than or equal to n, and the same with scalar multiplication. Watch my videos on polynomials. N by m matrices with real entries. Again, those are an example of a vector space. There are other ones. Functions from R to R. Functions that their domain is R and their codomain is R. I have a whole video on those. Those form a vector space as well. More generally, if X is any set, all the functions from X to R, those form a vector space also. The complex numbers, you can add the two complex numbers together and multiply by scalars by real numbers and get a complex number, and they form a vector space. So vector spaces are quite a varied bunch. And these are examples of vector spaces. There are plenty of vector spaces that other than these that you might run into. So a vector space is a set of elements where we can add and multiply by scalars, and the addition and scalar multiplication follow certain rules. Now, what's a vector? It's any element of a vector space. That could be a polynomial, a matrix, a function, or complex numbers, or a number of other things. Anything that's an element of a vector space is a vector. You have to tell from the context what that is. Sometimes, again, the operations are not so obvious. In fact, I will have a video on a weird vector space where the operations are quite unusual, and you will have to check the properties quite carefully. Linear algebra is the study of vector spaces. What does that mean? That means that you don't study particular vector spaces. You don't study Rn or polynomials or matrices or functions or complex numbers. You try to understand all of them at once by focusing on vector spaces in the abstract. Just this set where you don't know what the elements are, but you know that there's two operations, an addition and scalar multiplication, but you don't actually know what they are. You just know that there are those games you can play, and those games follow certain rules. Given that, what can you say about a vector space? But why would you do that? First of all, it's versatile, and because of that, it has wide applicability. If you can say something profound about vector spaces, once and for all, you've said things about Rn, about polynomials, about matrices, about functions, about complex numbers, and so forth, and many other things. But more important than that is that you are throwing out information. By throwing out information and focusing on just the vector space aspect of a mathematical object, we're able to understand those properties much better and be able to create connections. We see what Rn has in common with polynomials, what that has in common with matrices. If we know something in Rn, can we take that concept, that idea, and move it over to functions? Can we move it over to complex numbers? So we can draw connections between different objects, and we can generalize concepts from one word to other words, because, for example, know something we can do with polynomials. And then we ask, is that thing also also works for complex numbers and functions and elements of Rn or not? Can I take that idea and move it over to other worlds? Are there any downsides? The question really is that if you look at the properties that we mentioned, they seem to be quite weak. There's not much to them. The question is that if all you know is that you have a set of elements, you don't know what the elements are, you know that there's an addition and scalar multiplication, but you don't actually know what the addition and scalar multiplication are, and all you know is those silly rules, then can you say anything profound? You should reserve judgment on that. That's the purpose of a linear algebra course, to convince you that actually there's a lot of things you can say about a vector space. How do we understand vector spaces? How do we go about studying them? We use examples like the ones we have to gain intuition, but we can't rely on those examples because we want to say something in general about all vector spaces. And it might be that our intuition about one example doesn't really generalize to other examples. And so because of that, we have to prove everything carefully and from the ground up. We don't really know what all vector spaces are. We can't just check all vector spaces and see if what we want to say is true about all of them. Why do we prove things? First of all, we want to make sure that everything we say is correct and does apply to all vector spaces. But if that was the only thing, you could just say, we trust you. You're a math prof, so maybe you know what you're talking about. You do it, and then just tell us what's true. But that's not the only reason we prove things. The main reason we prove things is proofs make us understand. When you're trying to prove an idea, the process of figuring that out, you figure out exactly what the subtle parts of the definitions you made are, and what really is under the hood, and what makes something tick. Our purpose is to develop properties of vector spaces from the axioms step by step, and in that way we get to understand and get a good feel for what these properties do. I want to say a word about scalars. I have been saying that the scalars are real numbers for the first time through linear algebra. Whenever you hear the word scalars, you can think of real numbers. And we emphasize that by saying V is a vector space over R. But could scalars be anything else? In fact, they can. They can be any collection of numbers. In fact, they don't even have to be numbers. They could be other things with this property, where we have a 0 and a 1, and we can add, subtract, multiply, and divide by non-zero elements. 0 is something that when you add to things, nothing happens. 1 is something that when you multiply by things, nothing happens. Whenever you have a 0 and a 1, and you can add, subtract, multiply, and divide by non-zero elements, we call that collection a field. And scalars can be from any field. Examples of fields are real numbers, but they're also complex numbers, rational numbers, and many others. We will have later videos on finite fields that have only a finite number of elements. So scalars can actually be a multitude of different things. When you go through linear algebra a second time or a third time, those scalars might take center stage. That's the end of this lecture. Like my video if you liked it. Subscribe to my channel if you want to be subjected to more undergraduate math videos, and keep hydrated at all times. I will see you at the next lecture.